Here is another summary video for Diploma Program Physics. This time we're going to be talking about topic 11, which is a high level topic, electromagnetic induction. And the main concept, if you like, is if we were to have a wire moving in a uniform magnetic field, so the wire is moving to the right with a velocity v and it has a length L, and because there's a force on the electrons downwards, there's going to be a electric field and therefore a potential difference set up in the wire, and the induced EMF, the induced electromotive force, is equal to the magnetic field strength B times the velocity v times the length of the wire in the field L. We also then need to define a new quantity which is involved in Faraday's law, and that's magnetic flux and magnetic flux linkage. The symbol for magnetic flux is the Greek letter phi, and it's measured in Weber. It's basically the magnetic field B times by the area of the coil perpendicular to the magnetic field A. So to find phi, we take B, the magnetic field strength, we multiply that by the area of the coil times by the cosine of the angle between the B field and the normal to the plane of the surface. And phi is 0 when theta is 90 degrees, but likewise phi is maximum when B is perpendicular to the surface of the coil. Magnetic flux linkage is simply the magnetic flux phi multiplied by the number of turns on the coil. Now Faraday's law says that the induced EMF, this quantity here epsilon, is proportional to the rate of change of magnetic flux. So the greater the rate of change of magnetic flux, the greater the induced EMF. And from a graph of magnetic flux against time, because induced EMF is the rate of change of magnetic flux, that's interpreted as the gradient at any instant in time of the magnetic flux time graph gives us the EMF. So if we had a graph of magnetic flux against time which looked like this, that would interpret to a graph of EMF, induced EMF against time, which looks like this. Finally, Lenz's law, which is based on the principle of conservation of energy, states that the direction of the induced magnetic field acts to oppose the change in magnetic field. So if we have a coil and we have a bar magnet falling through the coil, as it falls from above, the magnetic field strength increases as it approaches the coil. You can see that because the field lines are getting closer together. Therefore, the induced magnetic field acts to oppose that change and is directed upwards. Therefore, from the right-hand grip rule, the induced current is going counterclockwise. However, as the coil leaves from below the coil, the magnetic field is decreasing downwards, so the magnetic field acts to oppose the decrease by increasing downwards, and therefore the current switches direction. But remember, Lenz's law is a result of the conservation of energy.